Okay, this is Unit 3, Video 5, Orbital Diagrams. So at this point, we've drawn electron configurations which have covered the quantum numbers N and L. Now, the two quantum numbers that we're missing are M sub L and M sub S. So we're missing our orbitals and our spin. So the way we're going to do that is we're going to first draw the electron configuration, and then from that we can draw our orbitals, which we classify as the orbital diagram. So if we do something simple, such as let's do nitrogen. So we know nitrogen has 7 electrons. So if we were to draw the electron configuration for nitrogen, we would get 1s2, 2s2, 2p3. Okay, we know we need to have a total of 7. 2 plus 2 is 4, 4 plus 3 is 7. So we've got 7 electrons. Now, a real quick summary for our orbitals. Everything in the S, whenever we have an S, we're going to draw 1 orbital. For the P, we're going to draw 3 orbitals. For the D, we're going to draw 5. And for the F, we would draw 7. So all we do for orbital diagrams are for each of our sub-energy levels, we're going to draw however many orbitals we need. So here, for our 1s, we need one orbital. We're going to classify this as the 1s, and we're going to fill our electrons. So we've got 2 electrons. The way we fill is we fill first, and then we come back. So we've got 1 spin up and 1 spin down. Then we go to the next one, which is our 2s. We've also got 2 electrons there, so we're going to do the same thing. Then we've got our 2p, which our p is going to have 3 orbitals, which we know this is to be -1, 0, and 1 for our quantum numbers. So we're going to have 3 electrons. Hund's rule said we fill first and then we come back through. So we've got 3 electrons, we're going to fill up. We don't have any more electrons to come back around, so we're going to stop there. So this would be the orbital diagram for nitrogen. Now, if we normally, let's say we have a big element such as antimony, which is 51, we're not going to draw 51 electrons and put them into an orbital diagram. We tend to use the noble gas abbreviation because all we really care about are the valence electrons. The core electrons are important, they're what make the atom whatever the element is, but what we care about in the reaction is going to be the valence electrons. So here if we look at antimony, let's go ahead and draw the abbreviated electron configuration for antimony. So we're going to go to the previous noble gas. The previous noble gas is going to be krypton. So krypton is going to cover antimony's core electrons. Then we're going to count after we get to antimony. So krypton is on the 4th energy row, so we're going to start with the S. So we're in the 5s2, and then we're going to come across, and we're now in the 4d. So this is 4d10, and then we're going to come across, here we're at cadmium, and then at indium we are now in the 5p column. And 5p, we're going to count until we get to antimony, so this is going to be 5p3. So all we care about drawing for the orbital diagram is going to be our valence electrons. So we're going to go through. First orbital is going to be the 5s. We've got 2 electrons in there, so we're going to pop those in there. Now our d has 5 orbitals. So we're going to have a 1, 2, 3, 4, 5. Excuse me, we're going to call this the 5d. I'm sorry, not the 5d, the 4d. Now, the way we fill for Huns is we fill first and come back through. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to go to the 5p, which has 3 orbitals. So 1, 2, 3. And in the 5p, we've got 3 electrons. So we're going to fill up. We don't have any more to come back around. So that's going to be the completed orbital diagram for antimony. So in general, the orbital diagram is just going to cover the other 2 quantum numbers that electron configuration doesn't cover. So if we have electron configuration with the orbital diagram, we have all the quantum numbers, which is going to tell us where the electrons are located.